During the homework and stuff, I just realized how does heat transfer through ultraviolet? Because technically they're too far from the sun. We still get the heat from them. So is this because of the ultraviolet enter the atmosphere that's causing the heat?
Yeah.
Or because it took like I believe it took like 7 minutes something
Yeah.
when the sun disappeared, and then we can actually know that the sun's gonna travel to us like that for the timelines and stuff.
Yeah.
So ultraviolet is the cause of the heat as well, or is this?
Yeah. So that's a type of heating called radiation. So we're going to cover that probably near the very end of the class. So that's basically how heat goes from the sun to
So
the earth.
technically, radiation is just wave that's
Exactly.
causing the heat.
Exactly.
Because
Yeah.
of vibration.
Exactly. Because energy can travel through electromagnetic waves. And so anytime you transfer energy, it's considered radiation heat transfer. But for your case, you know, there's probably a little bit of, because the radiation also heats the atmosphere a little bit too. And so probably there's a mixture of, you know, the radiation heating the atmosphere and the atmosphere heating up the plane. But then you know, because the plane is so high up, it's also absorbing radiation from the sun too. Yeah, so probably a little mix of both.
Yeah, that's what I was like. It's too far. How can it's heat? Because it doesn't transfer good in air, and then space is just a bunch of non-solid ones. So the solid, liquid, and then air. So air will be released in heat transfer, right?
Right. Yeah.
How's it?
Yeah. It's probably radiation. Yeah.
Or something in the space we don't know yet.
It's probably from the sun. It's just
Yeah.
radiation.
Is that not pressured? So the space is no pressure, right?
Exactly. Yeah.
So is this better with it no pressure and the heat wave gonna transfer faster?
It's not about pressure. It's more about matter actually.
matter.
Because technically in air there are still molecules. There's a monomolecule. And so those molecules can transfer heat through conduction or convection.
Yes.
But in space, you know, there's no matter at all. It's just empty.
Empty.
Right. So in those cases, radiation does transfer better because there's less molecules that kind of refract or kind of block the radiation. But also, you know, in space, in a vacuum, that's the only kind of heat transfer you can get because it's impossible to get conduction or convection in a vacuum. So yeah.
You're the only person who want to be the chat. Why? You want suffering? Yeah. No, that's awful. And then being that I wasn't supposed to do it now. No, the other week been had. I want to bring free on bill. I don't know. That's great. What's up, Dr. Rand?
How's it going?
Good, how are you doing?
Good?
You're not cold?
No? I was bundled up before this, so.
You're welcome. You're welcome.
It's like they almost match. See? That's three counts. It's like, it's still like, but yeah, I was like, dedicated.
I don't know if it's not true.
Yeah. I haven't got some of the ones each of them.
That's all.
Bro.
No, you won't. If we had any sort of steering on it, I'd be kind of like. What was that?
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Keeping dry, hopefully. It's really raining a lot, but we need it, so it's good that we're raining right now. Okay, so plan for today, we're gonna keep talking about fins. So last time we were here on Tuesday, we introduced the concept of a fin. We did a little bit of equation stuff, but we're just gonna dive deeper into that. I have one example to do with the fin as well. And then I'm hoping we can talk about 2D conduction and shape factors today as well, just to kind of round out just this these lecture notes. Okay. All right. Any questions I can answer before we get started? Yep.
Whenever we have something like, say, for example, a sphere or a cylinder where there's multiple layers,
Mhm.
and then we were talking about the critical thickness.
Yep.
Where the critical thickness, it has the thermal conductivity in it.
Mhm.
What is the thermal conductivity if there's multiple thermal conductivities?
Yeah, so in those situations, you would have a separate resistor for each layer. Also, I guess, for people on Zoom, the question is, if you have a cylindrical or spherical system with multiple layers of different material, what does the thermal conductivity kind of represent in that situation? So let me actually draw it. It might be a little easier to draw. So if you have kind of a cylindrical system like this, right? Right, so let's say we have 3 layers here. So we have Ka, Kb, Kc, right? So 3 different layers, 3 different materials. In this situation, you would use a different resistor for each layer. So each layer you can plug in a different value for K. So let's say this is a sphere. So the thermal resistance for a sphere is 1 over Ri minus 1 over Ro divided by 4 pi K, right? So here's where you plug in for K, but then for each layer, you would just plug in a different value for K for each one, right? So for layer, we'll call this layer A, layer B, layer C. You'll have separate values for Ra is equal to, let me draw on some resistance, some radii here. So we'll call this R1, R2, R3, R4. So the resistance for layer A is 1 over Ra minus 1 over, I'm getting my numbers and letters mixed up, 1 over R1 minus 1 over R2 divided by 4 pi Ka, because Ka, that's the thermal conductivity of that particular layer. And then you have a separate resistance for layer B and layer C. And then when you draw your whole circuit, you'd have 3 resistances. One resistance kind of represents each layer. So Ra, Rb, Rc, right? And then for each one, you can plug in a different. Yeah. Does that answer your question?
Oh, just because I was talking about like the critical thickness.
Oh, critical. I'm sorry. I missed that one. So for the critical thickness, you would only do it for the outermost layer here. Yeah.
Okay.
Yeah, because then for the other ones, they they're not on the outside.
Okay.
Yeah.
Okay.
I'm sorry, I misinterpreted your question.
It's okay. It's okay. Thank you.
All right. Any other questions before we get started? Okay. All right. So let's go ahead and get rolling. Okay. So what we were talking about last time was this idea of a fin. Okay. Fin is just kind of a short word to describe what we call an extended surface from a system. Okay. So a fin is something that is very common because if you work on the thermal side of these complex engineering systems, a very common issue, a very common problem that you're going to have is that your system is just producing just too much heat. So whether you're working on an engine or where you're working on electronics, so there's a lot of heat that you need to offload to the environment in order to keep your system cool. And so one way or one strategy that's often employed to do this is to basically increase the effective surface area of your system so that there's more opportunities or more surface area for convection cooling to occur. Okay. So that's the entire premise of a fin or an extended surface is to, basically make these structures or make these, things to increase the surface area so that more convection can occur to cool your device or to cool your system. Okay. Now, we're going to be developing this theory mostly for a singular fin, right? Where, this is the X direction, we have the cross-sectional area, and we have the surface area as well, right? So, all the theory that we're developing is for just a single fin, just because it's easier. But in reality, usually you want to build multiple of these. And so, it would look a little bit strange to have, your engineering device in just one single kind of, thing that's coming out as a single fin, right? Okay. So this is probably a lot more common that you're going to see in a lot of engineering systems where you have a bunch of these kind of fins or extended surfaces that are coming out, right? And so you'll have multiple fins. If you look at it from the side, it might look something like this. Okay. If you look at it from above, you might have multiple fins that are kind of stacked, kind of like this, right? So this would be like the side view, top view. Okay. Okay. And then what's going to happen in these situations is that air is going to flow, through these fins, okay? Or some kind of fluid is gonna flow. Usually it's air, just because your device is probably exposed to air at some point. Okay. All right. So just because of time, we're not going to get into the theory of having multiple fins kind of stacked together. We're mostly just going to focus on one. But I did want to highlight this to you just so that at least for me, one thing that I really enjoy doing when I learn something new is I like to go see kind of how it's applied in the real world. And so I did want to mention this just because if you're going to look inside your engine, you're going to look inside your computer, you're not going to see a single fin like this, even though all the theory that we're going to produce is or all the theory that we're going to discuss is mostly just for a single fin. You're going to have multiple, but just know that a lot of the theory or a lot of the intuition that we're going to build up from the single fin applies for multiple fins as well. Okay. It gets actually really interesting because how you arrange your bank of fins can affect the airflow through the fins, and that's going to affect the convection heat transfer as well. So there's a lot of really interesting theory there too. It's just we don't have enough time to kind of go through it. But I did want to mention that before we get too much into the weeds of the calculations. Okay. Okay. So that's where we're at. So we are looking at fins, and so we want to develop some kind of theory or some kind of some concepts so that we can better understand fin performance and how to enhance what aspects of the fin are going to lead to better heat transfer or better performance. Okay. So that's one of the main questions that we're going to answer today. And I want you to kind of keep that in mind as we're kind of going through the equations and deriving stuff. Okay. All right. Any questions on this so far? Okay, good. All right, so let's pick up where we left off last time. Okay, so last time we were right in the middle of deriving the fin equation or the fin heat equation. Okay. So the fin heat equation looked like the following. So we had d squared T dx squared minus h times P divided by K AC multiplied by T minus T infinity. Okay. All that's equal to 0. And then right before we left, we said that, while this equation, we can solve this equation, this one is perfectly valid to solve, but to make it a little bit easier or very slightly easier for us, we're going to make a change of variables. Okay. And so the change of variable that we're going to do is we're going to substitute in for t. Okay. So we're going to define this new quantity called theta. So this theta is what's called the excess temperature. Okay. And what this is this is equal to the difference between the temperature at the fin or in the fin minus the fluid temperature, T infinity. Okay. Okay. And so what this is going to allow us to do is that it's going to allow us to plug in directly for this quantity right here. Okay. So this theta is just going to slot in right there. What that does is that it's going to make this equation homogeneous, which is nice, which is good. Okay. And because the change of variable that we're doing is essentially just an offset, you know, we're not making any kind of multiplicative change of variables. It's just a subtraction. When we take the derivative of theta, excuse me, so we take the derivative of theta, okay, second order derivative of theta with respect to x, okay. Since T infinity here is assumed to be a constant, when we take the derivative of this, all we end up with is d squared t dx squared. Okay. Which means that, you know, we can just plug this right in for the second order derivative up here. Okay. All right, so if we perform that change of variables, we end up with the following. So we get d squared theta dx squared minus HP over KAC multiplied by theta is equal to 0. Okay. All right, and then what we have here is we have a second order linear ordinary differential equation with constant coefficients, right? And so this is something that we can solve. And so if you think back to your 250B class or your 308 class, this is one that we can solve using the characteristic equation. Okay. And so the characteristic equation, remember, we basically are going to solve for the roots of this equation, right? So for every derivative here, we're going to replace it with a I use the symbol lambda. So for the second order derivative, we're going to replace it with lambda squared. Okay. And then there's no first order derivative terms. So we don't have any lambda terms. Okay. And then we're just going to do minus HP over KAC is equal to 0. Okay. Okay, so let's solve for the roots of this characteristic equation. This one's pretty simple. We don't need the quadratic formula for this. We can just add HP over KAC to both sides and take the square root. Okay. And so we get lambda is equal to plus or minus square root HP over KAC. Okay. That means lambda 1 is equal to positive square root HP over KAC, and lambda 2 is equal to negative square root HP over KAC. Okay. All right, so now that we have our two roots, we can form our general solution, right? And so the general solution to this problem, theta of x is equal to, since our two roots here are real, we're not going to have any oscillation, so there's no sine or cosine. And so we just have simple exponential solutions. So our theta of x is equal to C1 e to the lambda 1 x plus C2 e to the lambda 2 x. Okay. And again, this is because we have two real roots. Let's go ahead and plug in from lambda 1, lambda 2. We have theta of x is equal to C1 e to the square root HP over KAC times x plus C2 e to the minus square root HP over KAC x. And this expression that I've boxed right here is the general solution for the temperature distribution, or how temperature varies along the length of a fin. Okay. Any questions on how we got this result here? Okay. Good. All right, so this is a good start. And so we can see from here that our solution is exponential in nature, okay? But this is still just a general solution. And so this is not the full solution yet, right? And so if you recall from your previous math class, 308, 250b, at this point, in order for us to solve for the full solution, we need to apply boundary conditions and solve for the constants C1 and C2. Okay. So if you notice, that's kind of a big theme of this class is solving differential equations and applying boundary conditions. Okay. Okay. So what are the boundary conditions that we're going to apply in this case? And so, luckily, for this part, the boundary conditions aren't really going to change from problem to problem. I know that was kind of a point of, quite a few people kind of asked questions about the last two homeworks about that. But luckily for fins, we're only going to be looking at kind of one given situation. So these boundary conditions are going to be the same kind of for every situation that we look at. Okay. Okay. So for the first boundary condition that we're going to apply is we're going to apply a known temperature at the base. Okay. And the base of the fin is where x is equal to 0. Okay. So let me go ahead and draw our figure for our singular fin one more time. Okay. So our fin looks like this. We know the x direction goes down the length of the fin, right? The base of the fin is where the fin basically connects to your larger engineering system here. So this part where I've circled is where x is equal to 0. And so this first boundary condition is going to specify that we basically know the temperature at the base here. So when when x is equal to 0, theta is going to be something, we'll call it theta b, okay? Where theta b here, this is the excess temperature at the base of the fin. So usually this is something that's going to be known. So if you're designing a thermal system or you're designing a you're engineering a system that's going to require a fin, you probably have knowledge of what the surface temperature is, at the base of that fin. So this is usually something that's known. Okay, so this is not something we're making up, or not something that we're assuming. This is usually kind of known, in all situations that I can think of, for like for electronics, that's kind of where, I know a lot about this stuff. It's usually known what your surface temperature is, or at least you know what the worst case scenario for that temperature is going to be. Okay. Okay, so theta B here is nothing more than just the temperature at the base minus T infinity. Okay. Remember, this theta here is not temperature by itself. It's excess temperature. So you have to subtract the T infinity as well. Okay, so that boundary conditions is pretty straightforward. Okay. The second boundary condition pertains to the thermal condition, or the thermal situation at the tip of the fin. Okay. So we have one condition at the base. The other boundary condition is going to be at the very, very tip. Okay. Okay. So if we assume that the fin has a length L, okay, so that's the total length of our fin, then the tip of the fin is going to be when X is equal to L. Right. So at the tip of the fin, in reality, it gets a bit more complicated. So, we're going to skip most of it just because of time. But if you look in the textbook devotes like 10 pages to the different tip conditions. So I would say at the tip of the fin, it can be complicated. Right. In fact, I actually have it in my notes here. So it's actually 5 pages of just math and derivations, which we are going to skip. So, it's just because I think it's one of those things where we can go through the math, and you guys can, it's not a question of you guys can do it or not. You guys can definitely do it. But I think some of the important messages that I wanted to share about the fins kind of gets lost in the sauce a little bit. So, so we're going to focus on just kind of the simplest tip condition. Which actually, it's actually pretty reasonable, and this is one thing where, it's the simplest one, but, it's also one that usually makes sense in a lot of cases too. Okay. So the tip condition that we're going to be assuming is that we're going to assume that the fin is sufficiently long. Okay. Right, so let me go ahead and draw the fin here. Okay. So what does it mean for a fin to be very long, or how does that actually help us? Question, yes.
So like it's not heat soaked and it's like a gradient all the way through kind of thing?
Close. I think you have the right idea. So when the fin is very long, basically what's going to happen is that at the very tip, if the fin is sufficiently long, at the very tip of the fin is going to be the same temperature as the fluid. And so it's basically going to lose enough heat so that the tip is the same. Okay. Okay, so why is that the case? And so think about kind of intuitively what's kind of happening. And so, when you have a fin like this, most of the time, there are reverse situations too. You know, there are some situations where you use a fin to actually heat up your structure, but the vast majority of cases, you have a very hot base, right? So theta B here is very large. Okay. So in most cases, you know, you're gonna have a large base temperature, and your fin is going to be cooling. Okay. As you go along the fin, right? What's happening is that the fluid is passing over the fin itself, right? And a lot of that heat is actually leaving the fin. It's going into the fluid, right? So as you go along the fin, you know, what makes sense is that the temperature in the fin is actually going to drop down the length of the fin, right? So at the very beginning right here, your temperature is very high, okay? But then as you go along, it's going to become, I should have picked a number, but you know, instead of high, it's going to be slightly less high. Okay. And then less high. And then maybe, I did not plan this well, medium, and then low. Okay. So obviously I didn't draw this fin long enough, because the fin should be long enough so that as you go along, as the temperature decreases more, eventually it's going to decrease to the smallest it can possibly be. And the lowest the temperature can possibly be for this fin is the same temperature as the fluid, because it's impossible for the fin to reach temperature lower than the fluid. Okay. And so if you have a really long fin, what we say is that at the tip of the fin just reaches the same temperature as the fluid. Okay. Okay. So mathematically, this actually is quite simple to implement. Because what we're saying is that at the end, the temperature, when x is equal to, or let's be a bit more strict here. So the temperature as x approaches infinity is going to be equal to T infinity, right? And so what this means is that the excess temperature as x approaches infinity is going to be 0, right? Remember, excess temperature is just the difference in temperature between the fin and the fluid. And so if the tip of the fin matches the temperature of the fluid, the excess temperature must be 0. Okay. All right. Any questions on the tip condition here? Okay. All right. So those are our two boundary conditions. So we have this guy, and we have condition 1. Let me write it again here too. So condition 1 is theta when x is equal to 0 is equal to theta base. Okay. Okay, so let's apply these two conditions to our general solution. Okay. So our general solution, theta of x is equal to C1 e to the positive HP over KAC x plus C2 e to the minus square root of HP over KAC x. Okay. Okay. So by applying these two boundary conditions, we can solve for our arbitrary constants C1 and C2, right? Let's actually apply the tip condition first, because that one's actually the one that's going to simplify things the most. Okay. Okay. So if we apply our tip condition first, we're going to say theta as x approaches infinity is equal to 0. Okay. So let's plug in x. Well, we can't plug in x is equal to infinity, but you know, let's just say that we're going to take the limit as x approaches infinity. Okay. So we're going to take the limit as x approaches infinity of C1 e to the positive square root HP over KAC X plus C2 e to the negative square root HP over KAC X. Okay. Okay. So one of these terms obviously is going to blow up, right? And so if we look at the first term here, right, we have an exponential with a positive exponent, right? And so as x goes to infinity, this also goes to infinity. Okay. Whereas if you look at the second term, we have an exponential with a negative exponent here, okay? And as x goes to infinity, this is actually going to go towards 0. Okay? Right? So we have two exponentials, and they do very different things as we approach infinity, or we approach the tip. Okay. All right. But our boundary condition here states that as x approaches to infinity, our excess temperature is going to go to 0. Okay. And so there's one part of this solution that's incompatible with that boundary condition, which is the C1 term. Okay. And so in order to make this compatible, just like we did when we solved the the heat equation for a solid cylinder or a solid sphere, this term just cannot exist. And so we have to get rid of it. And so from the tip condition, we know that C1 has to equal to 0. Okay. And so by doing that, our general solution now is theta of x is equal to C2 e to the minus square root HP over KAC times x. Okay.
Can you explain how C1 is equal to 0 one more time?
Sure. So we know from our tip condition that basically our temperature at x is equal to infinity has to be finite, right? Because we're assuming that our fin is really, really long, and we have to have some kind of finite solution there. And so that C1 term has a positive exponential. So as x goes to infinity, that term is also going to blow up. And so in order to be consistent with this, C1 has to be 0, or that term just can't exist. Yeah. All right, any other questions on this part here? Yeah.
What does P represent again?
P is the perimeter.
I have a question, but I feel like it'll be answered if we were to do like an example with numerical values, or we're going to do an example.
Yeah, we're going to do an example with numerical values after this. Yeah.
Thank you.
Yeah, we're almost done with the derivation.
That second exponent is negative, right?
Yeah, second exponent is negative. Okay, so let's apply the base condition now, and then we're going to do an example right after that. Okay. So our base condition is theta when x is equal to 0 is equal to theta b. Okay. So this one's pretty straightforward to apply, because when we plug in x is equal to 0, the exponential term there just goes to 1, right? And so we have theta at x is equal to 0 is equal to C2 e to the 0. Okay. That's equal to theta b. And so that's going to go away, or go to 1, excuse me. And so C2 here is equal to theta b, right? And so our final solution theta of x is equal to theta b e to the minus square root HP over KAC x. Okay. So all that worked for a very simple solution, I guess you could say. Okay.
Stop there, E to the what?
Well, it was e to the 0, so we just say it's equal to 1. Yeah. Okay, so let's put some numbers on this. And so we've been going through derivations for a while. So let's see what this looks like in a problem. Okay. Okay. Now, one thing that you have to consider a lot for the fin. So all the theory that we just covered, you know, we haven't really made any assumptions on the cross-sectional shape of the fin itself. Okay. But that can actually play a really big role. And so when you see, you know, when you look at examples or problems with fins, you know, the problem will usually tell you kind of what the cross-sectional shape of that fin is, right? So for this example, let's do kind of a very simple case. And so let's look at a cylindrical fin. So a cylindrical fin has a circular cross-section. Okay. So our fin is going to look like this. Now we're being a bit more clear about the cross-section because it has, it's a cylinder, okay? Let's say the diameter of this fin is 5 millimeters. Okay. Let's say it's made of a material with a thermal conductivity of 180 watts per meters Kelvin. Okay. So it's a fairly conductive fin. It's probably made of some metal of some kind. Okay. Let's say that the temperature at the base. Now this is just flat temperature, so it's not excess temperature. So I say the temperature at the base is 100 degrees C. Okay. And let's say the fin is cooled by ambient air. Okay. And the air has an ambient temperature of 25 degrees C with a convection coefficient of 100 watts per meter squared Kelvin. Okay. By the way, I think this may be the first time that I'm doing this in the class, but you know, notice how in the denominators for these I'm doing K. This K here stands for Kelvin. I think in previously I put the units as degree C. So degree C and Kelvin are interchangeable, but I think this might be the first time I did it in the class. So I just kind of wanted to make that clear. Okay. So for this fin, let's make the assumption that the fin is sufficiently long. Okay. And so the tip condition that we assumed in the previous part is going to be valid here. Okay. So let's answer the following questions. Yeah. So this K here, this is thermal conductivity. Yeah, so thermal conductivity should be lowercase k, and Kelvin K is uppercase K. It's just that it's hard to tell because my handwriting is so poor. But if the K is kind of on the right on the units here, that stands for Kelvin. On the left-hand side, it's thermal conductivity. So actually, let me make this a bit more clear. So instead of Kelvin on the bottom here, let me change this to degrees Celsius. Right. But on the homeworks and stuff, you may see Kelvin K. So just kind of be aware of that. Yeah.
They are equivalent in magnitude, is that right?
Yeah, so they're just offset from each other. So temperature in Kelvin is equal to just whatever is in degree C plus 273.15 or something like that. Yeah.
But the actual like K, you wanted to go from degrees to Kelvin, you just keep it as 180, right?
Oh yes, yeah. And so the value of thermal conductivity or convection coefficient doesn't change whether it's Kelvin or degree C.
Okay.
Yeah. Mm-hmm. Okay, so let's answer the following questions. And so first one is, let's solve for the temperature distribution in the rod. Or I guess the fin, I should say. Right. Number two, let's compute the total amount of heat transfer from the fin. And then number three is going to be an interesting one because we've kind of solved for the solution to the fin equation, assuming that our fin is sufficiently long. And so part three of this problem is let's solve for what the theoretical length of this fin should be in order to make that assumption valid. Okay. So how long does the fin have to be? Because those words kind of get thrown around a lot, sufficiently long, sufficiently small, infinitesimally small. So let's actually compute it. So let's see kind of what that means in this case. And mathematically, how can we kind of show that? Okay. Okay. All right, so let's start with the temperature distribution. This one is pretty straightforward because we've kind of already solved for it. Okay. So the temperature distribution in a fin is given by this, what we just kind of finished deriving here, okay? So theta of x is equal to theta b multiplied by E to the minus square root of HP divided by KAC times X, okay? That right there is our temperature distribution, or I guess more specifically, it's the excess temperature distribution. Okay. And so to get the full distribution here, we just got to plug in for all the numbers here. Okay. Okay. So quantities like H, the convection coefficient, and K, those are already given to us in the problem. So there's nothing additional we need to compute there. We just plug it in. But we do need to compute values for theta B, for the perimeter, as well as the cross-sectional area. Okay, so let's start with theta B. That's the simplest one. Okay. So theta B here, remember, this is the excess temperature at the base. Okay. Okay. So in the problem, we're not given the excess temperature at the base, we're given the temperature at the base, right? So if we go back to the problem here, we know that the base temperature is 100 degrees C, okay? And so the excess temperature there is going to be 100 degrees C, which is the temperature at the base, minus T infinity, okay? Where T infinity is the ambient temperature of the air, okay? All right, so we have 100, ambient temperature is 25, so we just have 100 minus 25. And so excess temperature here is going to be 75 degrees C. Okay. Okay, that one's pretty straightforward. Let's compute the perimeter next. Okay. Okay. So the perimeter, remember when we first started this example, I told you that fins can come in lots of different shapes. In this case, we have a circle, right? And so the perimeter here is going to be nothing more than just the perimeter of the circular cross section. Circumference, yes. Mhm. Okay, and so since we have a circular cross section here, the perimeter is just going to be the circumference of a circle. Okay, so that's going to be pi. We're actually given the diameter in this case, so it's going to be pi times the diameter. Okay, and I actually don't have that written, but that's pi times the diameter of 5 millimeters. So 5 millimeters is 0.005 meters. Okay. And we're going to compute everything in a standard SI. So actually, let me compute this really quick. Okay, so the perimeter here is 0.0157 meters. And then the cross-sectional area, we're just going to take area of a circle, which is pi r squared. We're not given r, we're given d. So it's going to be pi d divided by 2 squared. Okay. And so that is 0.0025 times 0.0025 times 3.14159. So this is 0.00001963 meters square. Okay. Okay. So let's plug all that in. And so let me compute the exponent first. So the exponent is square root of HP divided by KAC. Okay. So we just computed P, we just computed AC, convection coefficient H, thermal conductivity K are all given to us in the problem. And so this, we plug everything in, we get 21.08. Okay. And the units for this, if you're curious, is meters minus 1. So it's 1 over meters. Okay. So we have all of the numbers here. Let's just plug it all in. So our temperature distribution theta of x is equal to 75 e to the minus 21.08 x. All right, any questions on this part here? Okay, so that's part 1 of the problem. Part 2, now that we have the temperature distribution, we can compute the heat transfer rate or the total heat loss from the fin. Okay. All right. So for heat loss, we're going to make use of our handy dandy formula that we've used a lot this class already. Right. So now that we have a formula for the temperature distribution, finding the heat loss is just making use of Fourier's law. Okay. So Fourier's law states that the heat loss or heat transfer rate for a given problem is equal to minus K times A dt dx. Okay. Okay. So of course, we don't have T, we have theta, but T and theta are essentially interchangeable here. Okay. So let's take the derivative of theta, which is minus K A d theta dx. Okay. And this is actually a formula that's actually very useful. So actually, I'm gonna do this in terms of the general theta. Okay. So if theta is equal to theta b e to the minus square root HP over KAC. times X, okay? If we take the derivative of this, this is equal to minus theta B square root HP over KAC e to the minus square root HP over KAC times X, okay? All right, so let's go ahead and plug that in. Okay. And so we plug in for this, we get Q is equal to minus K. That area there is cross-sectional area, so we're just going to do KAC multiplied by our derivative. We're just going to drop this guy in here. Minus theta B square root HP over KAC e to the minus square root HP over KAC times X. Okay. Yeah.
Why don't you use the general solution that you just solved?
So this formula for the heat transfer, it's going to be useful for every problem. So we're deriving it just from the symbols, and then we're going to plug in the values from this problem afterwards. Yeah. Yeah, because in the homework, you'll see that, there'll be questions of, how do you, compute the total heat loss? And I'd rather you just have a formula that you can just plug in for this instead of deriving everything. Yeah. Mhm. All right, so let's simplify this. And so if we simplify this, the negatives are going to cancel out. Okay. So we have a KAC up top here and a KAC under a square root on the bottom. So actually, if you work this out, we're going to get Q is equal to theta B square root. So that KAC actually goes within the square root there. So square root of HP KAC, okay, e to the minus square root HP over KAC X. Okay. Okay. So this is good, right? So we've simplified this expression quite a bit, but it's still not the easiest to work with right here, okay? Because what do you notice here, right? So this is an expression for Q, right? So this is an expression for heat transfer rate or heat loss. Okay. I should say heat transfer rate in the fin. Okay. But if you look at this expression here, we still have a dependence on X, right? And so the fact that this term here still exists means that the heat transfer in the fin changes as you go along the fin. All right. And so if you remember the figure that I kind of drew earlier where the temperature kind of changes, it goes from high to slightly less high to less high to medium, right? Because the temperature is dropping along the fin, that means the amount of heat transfer, as you go along the fin is also going to change, okay? So if we draw it out, right, we draw our fin just like this, okay? We have air that's coming blowing through it. So if we compare, so let's compare, 5 different values of Q here along the fin. Okay. So I'll call this Q1, Q2, Q3, Q4, Q5. Okay. And so if we go based on the formula above there, that means the instantaneous amount of heat transfer that's coming out depends on where you are located along the fin, right? So Q1 here is going to be greater than Q2, which is going to be greater than Q3, which is going to be greater than Q4, which is going to be greater than Q5. Okay. So most of the heat transfer or most of the heat loss is going to take place at the base of the fin. And then as the fin kind of cools down as it goes along, there's going to be less and less heat transfer. Okay. And that makes sense, right? Because we know that the temperature is going to be highest at the base. And if we follow the cardinal rule of heat transfer, if the temperature difference is highest at the base, that means that the heat transfer there is going to be the highest as well. Okay. Okay. But that makes hopefully that makes sense, right? So the more temperature difference you have, the more heat transfer is going to occur. This formula, because of that, is not that useful to us because it's still a function of x. So what we would like to see is that if we could get a formula that just basically computes the total amount of heat loss from this entire fin. Okay.
We tried. Actually, like this for our next.
took me a second. I was like, yeah, we can. Like, wait a second. Okay, because ideally, we have all the numbers for this fin here, and so it would be ideal is if we can just compute. This fin is going to lose this amount of heat, and so we can just put a number on it. Okay. Turns out we can't. And we can do it by just making one very simple kind of plug in, okay? Or I would say one very important kind of observation, and that will allow us to plug something in. Okay. So this fin, is made of some kind of material that is, 100% of the time is going to be some kind of inert material. And so it's not going to be material that's going to be producing heat, okay? So if we kind of remember that, then all of the heat that's going to be, being lost from the fin has to pass through the base at some point. Okay. Okay. Because we know the fin itself is not producing any heat. The fluid itself is not heating it, right? The fluid is cooler than the fin. And so any energy loss or any kind of heat that's getting lost from the fin, has to come from whatever system you're trying to cool. And so every bit of heat must pass through this base at some point. Okay. Right. Because that's kind of what the fin is designed to do. The fin is designed to kind of take heat from your object, from your system, and then offload it to the fluid. Okay. And so what does this mean? And so what this means is that if we compute the Q at x is equal to 0, okay? What this does is this actually represents the total heat loss for the entire fin. And so that's really helpful for us because if we plug in x is equal to 0, then this expression here becomes quite simple. Okay. Okay, so if we plug in x is equal to 0, we get Q. And I'm going to box this equation, so I'll call this Q fin. Okay, so QF is equal to square root HP KAC times theta base, and that's it. Because when we plug in x is equal to 0, then that exponential term essentially just kind of goes away because it equals to 1. Okay. Okay. So this is great. So this right here, this represents total heat loss from a fin. Okay. Probably one of the most useful formulas that you'll get from this class, because it's, you know, something that you can compute just right off the cuff, right? So if you're designing a fin for a thermal system, you can see exactly how much heat loss that fin will produce based on its geometry and based on the properties of the material and the surrounding fluid. Okay. Okay, so if we plug that in, what we get is QF is equal to 5.6 watts. Right. Yes.
So I think kind of mentioning about how the fins can get really complicated, but if they are sufficiently long and you have multiple of them, you can't just like multiply per fin.
So this one right here would probably be the upper limit of the heat loss. So I think that's still useful. And so probably in reality, it's not going to reach this level of performance if you have multiple fins stacked together. So it wouldn't just be 5.6 times 10. Because, you know, it's going to depend on the airflow. The air is also going to heat up locally too. But this at least sets an upper bound. So this tells you, you know, if you need to offload, let's say 50 watts of heat, then you need probably at least 10 fins. So that can still be useful in those situations.
Ballparks.
Yeah.
Like the ideas.
Exactly. Yeah. All right. Any other questions on this here? Okay. So the last part of this example, kind of just the fun part here. So if you remember from the original example, this part asks, how long does the fin have to be considered sufficiently long? Because what's fascinating about this whole example is that, you know, we've done all these calculations. We actually even computed the total heat loss, and we don't even know how long the fin is at this point, or we haven't even specified. Okay. Okay. But this is obviously very important to know if you're designing your fin, right? So there's a difference between a fin that's, you know, 50 centimeters versus a fin that's 5 meters long. And so you want to kind of know these things. Okay. So remember, the assumption for a long fin basically states that as the fin, you know, if you evaluate the excess temperature at the length of the fin, okay, then this is going to be essentially 0. So in other words, the tip of the fin is the same temperature as the fluid. Okay. So in other words, you know, we need to solve for the value of x that's going to make this true. Okay. So let me write out our general solution here. So we have theta of x is equal to 75 e to the minus 21.08 times x. Okay. So basically, we need to determine what value of x is needed to make this go down to 0. Okay. Okay. So the thing is with the decaying exponential like this, it's actually impossible to get it down to exactly 0. I know we always make that approximation that an exponential with a negative exponent goes down to 0, but it never actually equals 0. So we have to kind of make an approximation here, okay? And so instead of 0, okay? So how small does that temperature difference have to be in order for it to be considered effectively 0? Okay. So instead of 0, let's plug in, let's say if the, and you can have different criteria too. This is just the criteria that I use. And so if that temperature difference is only 1% of the base temperature difference, then we say that that's effectively 0. Okay. So let's plug in 0.01 theta. Okay. So we have 0.01 is equal to 0.01 theta B is equal to 75 e to the minus 21.08 x. Okay. Okay. So let's solve for this. Theta B is 75. So actually both of the theta B's are going to cancel out. Okay. All right, then we have 0.01 is equal to e to the minus 21.08 x. Okay. Let's solve for x. And so solving for x, we take the natural logarithm of both sides. We have x is equal to natural log of 0.01 divided by minus 21.08. Okay. Right. So if we compute that, we plug in the numbers, we get 0.22 meters. Okay. Which is actually pretty reasonable, right? So, 0.22 meters, that's, 22 centimeters. Not super unreasonable. But remember, the diameter of the fin is only 5 millimeters. So, it's going to be a very long, slender fin. Okay. All right. Any questions on this? Yeah.
Should it be like a ratio?
Yeah, essentially it is. And so if the I kind of mix the variables here, but what we're assuming is that the temperature difference goes down to 1% of theta B. Remember, our original solution had theta B on that side too, so the theta B's kind of cancel out. Yeah. So we're basically solving for the point where the temperature difference is 1% of what it is at the base. Yeah. Okay. All right. Last thing that I want to cover, and then we'll kind of wrap up with fins. It's this idea of fin performance. Okay. So now that we have a strong understanding of fins, we can compute its temperature distribution and its total heat loss. We want to have some kind of metric or some way to rate, how well the fin is actually performing its duties. Okay. Okay. All right, because it's one thing to say that this fin is going to offload this amount of heat, but it's sometimes it's better to come up with just a performance metric, and in this case, it's actually quite simple to do. Okay, so the way that we rate this is through a metric called fin effectiveness. So I'm going to give you the general definition for fin effectiveness, but then we'll go through kind of the actual specific one for the long fin that we're considering. Okay, so fin effectiveness that's the symbol for that is epsilon f is equal to QF divided by HAC theta B. Okay. So this expression here is a ratio, okay? So this ratio actually represents the total heat loss from the fin. Okay. And then in the denominator, what we have there is the total heat loss from the surface if there were no fin in place. Right. So in other words, we're comparing a situation where we have our fin, okay, and this fin has a heat loss QF versus, let's say we just have a flat wall instead of that fin, right? But in that same section of area where that fin would have been, right, we're still going to get convection heat loss there, but it's not going to be as much, okay? So one way that you can interpret the effectiveness is you can interpret it as how much the fin is going to amplify heat loss, you know, by being present. Okay. All right. So for our case, we actually we can actually plug it in, right? Because if we plug in our expression for QF, right? Because we have derived one for a long fin. Okay. We can get a slightly more specific version of this, although this expression here is perfectly valid as well. So you can use this. In fact, this is the one I typically use when I'm doing calculations too. Okay. But if you want to plug in, because we have this expression up here for QF, right? We have this one that we just went over like 15 minutes ago. And so we get effectiveness is equal to square root KP divided by HAC. Okay. So this is effectiveness for a long fin. Okay. Yeah.
Previous one to this one for.
Yeah. So for this one, I just so the numerator in the previous effectiveness was QF. All I did was I plugged in this expression for QF, which is what we derived for a long fin. Yeah. So the theta b's are going to cancel out, and you're going to have some other terms cancel out as well. Okay. So we're just out of time, but let me give you just, because this is a ratio, right? And so I think the question everyone asks, like, what is a good effectiveness? So generally, if your effectiveness is greater than 2, this is usually pretty good. Right? Of course, you want to be higher than this, ideally. If you're closer to 3, that's actually much better. But as long as your effectiveness is greater than 2, that means your fin is actually doing something. If it's less than 2, then it's amplifying it a little bit, but it's not as effective, or it's kind of not worth the trouble, right? So you may want to think of redesigning your fin. Okay. And then one thing I want you guys to think about, especially for the next homework assignment, is that look at the values, or look at the parameters in this formula here, and think about how they affect the effectiveness. So how does the thermal conductivity affect it? Perimeter, the cross-sectional area, and the convection coefficient. Okay. All right, so that's all we got time for today. When we come back on Tuesday, we'll start talking about shape factors and 2D conduction. Hopefully that's not going to take too long. And then we'll move on to time-dependent conduction from there. Right, so thank you guys for coming today. I hope you guys have a good weekend. Stay dry, stay safe out there. It's wet and on the roads and stuff, so drive carefully, and I will see you guys on Tuesday.
No, it's a good. Oh, it's terminal. Oh, it's good. It's probably good. But that's very common, right? It's like, oh, that's.
Yeah.
So just want to build out there right now. So for this expression, you divide by the. No, just because. Here, it's like, already like this.
Yeah.
When you go over here,
Go to lab.
you know, to the new rate, it's like kind of executive.
Okay.
This is essentially a single law.
I.
So the temperature difference between moving multiplied by the area. So this actually nothing.
Yeah.
Explain.
Oh, okay, I see, and then the rest is just algebraic. I think I'm thinking.
Yep.
I have two times.
Yeah, because if you plug in zero, if you try to solve for this, you actually can't solve. You have to kind of make an approximation of something that's close enough.
Is it like?
So we basically want to solve. The temperature essentially, we're very close. Because if we plug in zero here, you can see that eventually we're gonna take the actual. Right, if we take the actual zero.
But then if I'm going over here.
We have to take something close to zero just so that we can get an argument. I just figured that out. But then we can also take like 5% actually. Exactly, yeah, so it's actually, so there should be a square root of this too. This square root of which you can. So to get that one.
Yeah, I think I just missed that number.
I'm gonna do it too, because they're, yeah, it's all in a big file, I'm gonna post it here. Then you wanted to go over. Okay. Okay, yeah, I'll post it. Yeah. You too.